gas up against the surface causes a force that pushes it over. So you have the velocity profile against the together with the viscosity, then you have the pressure, and so that is what's going to push us over and cause the interaction. So spell this wrong. Okay, here we go. Okay, so here's the two physics. Okay, I don't expect you guys to know these equations, but this is what COMSOL is solving. And fortunately, because we have modules, you don't really need to know these equations. What you need to do is know how to use the equations, which is typically the case. So for this is called the incompressible Navier-Stokes equation. And it looks like that. So in this equation right here, so this is the volume force right here. And so for example, if you have gravity acting, that goes here as an example. You have two equations here, and the two unknowns you're trying to solve for is pressure and velocity throughout the entire field. That's what you're looking for. Okay, so the u is the velocity vector right here. So you can see u right here all throughout, and here's pressure. That's density. That's rho. So that's a known. The viscosity right here, the dynamic viscosity, that is also known. Okay, but you're solving for the velocity vector and the pressure. In this equation right here, you have the velocity vector. So two equations, two unknowns, you're going to solve for that. And then this is the structural mechanics physics. Okay, here's the load that's being applied to that beam that's going to bend over. Okay, now this load right here is affected by the pressure and the velocity. Right? Okay, so those two things are being solved here. They're being plugged in here. That is how those two things are interacting with each other. Okay, through those two coupling variables. N right here is just a normal vector. So that just means that wherever the surface is, you have this normal vector right here that's acting on it. So it's acting perpendicular to the surface. That's for it. All right, so that's the physics that's being used in these two things. And again, later on in the semester, we will find out, like let's say later on, you come into possession of some equations, or you make up your own equations that you want to model, and COMSOL doesn't have it. We're going to find out how to actually import or enter your own equations. But someone already did it, and they packaged it into a module, and that's what we're going to use. So we don't have to enter these equations if they're already in there. But that's what's happening. Another thing we're going to take advantage of in COMSOL is when you have, so we're going to mesh the fluid. We're also going to mesh the structure, okay? Now, the thing is we've meshed structures before, but what's really interesting here is that as the structure bends, you can see here that the mesh here just follows the outer part of the surface. Okay? So as the structure just bends over, the entire mesh just bends over with it. Okay? However, for the fluid, it's a little different. It's a little more complex, right? So the entire fluid is going to sort of the meshing of the fluid is going to morph over, right? So think of, a good way to think about this is, pretend this is actually a spider web, like the blue is a spider web, okay? And you put your finger right here in the spider web, and you put another finger right here in the spider web. You take your fingers and go like that. The spider web will contort and bend to however you're moving it around, right? And that's what's going to happen with this. So it's called the arbitrary Lagrangian Eulerian mesh, okay? And so we're going to take advantage of that. Otherwise, probably I think how they did this before they started using this method is that every time the structure moved, you had to remesh the entire system and then update your variables to the latest state, and then it'll have another small deflection, and then you remesh it again, and you kept doing that over and over again. Here, the mesh follows the movement. Okay, so whenever you have something that does that, this type of moving mesh is really useful. And again, what you're trying to do is, I mean, there's many ways in COMSOL to do things. And so what you want to try to learn is what are the most efficient tools inside COMSOL to give me the most accurate answer. Okay, so here are the parameters that we're going to use for the geometry and the variables and the substance. Okay, so on this boundary, this is going to be the inlet. Okay, and so there's going to be a profile here on this inlet, and also it's going to change in time. So that profile, how do I want to do this? Okay, we can just plot it out. Okay, so and also for the fluid, it's going to have some initial velocity, 3.3 centimeters per second coming in. The height of all this right here is going to be 100 microns, and the width is going to be 300 microns. The density, well, this density of water, 1,000 kilograms per meter cubed. I think it's really like 997, but 1,000. So 1,000 kilograms per meter cubed. So yeah, so this is like one of those numbers that you guys should, you'd want to memorize, just because water's so common. Viscosity, we'll use that for the dynamic viscosity. For the structure, it'll have this height right here, have this width, so it's just 5 microns. It'll be located at 100 microns, so if that's the origin, then right there is going to be 100 microns away. The density of that material is going to be this, so we'll just set it in. I mean, again, we can go pick our own material properties because it has a library of them, and we've done that before, but we'll just key these in. And it has a Young's modulus, 200 kilopascals, and a Poisson's ratio of 0.033. Okay. Okay, so let's do this. Trying to see how I'm going to do this at the same time. Okay, so I'm just logged into my office computer, and so let's plot what those profiles look like so you guys have a sense of what it is. Now, this is just like someone's idea, right? You can put other profiles because it's an expression. Okay, so I actually started typing these things in already. So let's see here. Yeah, cool. Okay, so this right here is, for those of you who are not familiar with MATLAB yet, this right here is just a MATLAB code, okay? And so what this first one is, this keyword right here is linear space. So what it says is, make some data points that go from 0 to 4 and make 1,000 of them. Okay, that's all that this line does. And it stores it into t. So that's our time. So our time goes from 0 seconds to 4 seconds, and it divides it up into 1,000 pieces. Okay, that's what this part does. This part right here, I'm telling MATLAB to pop up figure 1. Okay, so it'll pop up on the screen. This next command, CLF, is clear figure. So if there was something on the figure before, it'll erase it. Okay, so it's going to pop up on the screen, then it's going to clear it.
And then I'm going to tell, and then I tell MATLAB to turn the grid on, because otherwise it'll just plot it without any grid on there. So I tell it to turn the grid on, and then I tell it to hold the grid on, because then after that I'm going to plot something. If I don't have a hold on and it plots, then it'll erase what's on there before. Okay, so I hold that, and then here's my plot. Okay, so I'm plotting these two things. So this right here is time. That's on the x-axis. This right here is that equation that I showed you guys on this screen right here. That's this equation right here. I put 10 in for you, okay? But that's this equation. Okay? And then in MATLAB, you should end every line with a semicolon, unless you want it to print on the screen. So I labeled the x-axis time, and I labeled the y-axis inlet velocity. Well, anyway, so and I run that, and I get this. So that's why it says time here, because of this. And it says inlet velocity. That's why it says it right there. My time right here, remember, goes from 0 to 4. So you see it going from 0 all the way to 4. It's having 1,000 points here. So it's quite smooth. Okay, but this is what the profile looks like. So it starts going really fast at first, and then it tapers down, and then it asymptotes to steady state. Okay, so that's how it looks like when the fluid is like going through. Okay, and I'll give you an example. Let's say I just do 100 points to 1,000 points, and I plot that. You see, it doesn't. It's not as smooth. I could do even less. I could do 10 points between 0 and 4. Yeah, see. So that's what that function is doing. Line space. Linear space. All right. So that's what that profile looks like. Now the other profile. Here's what you could do in MATLAB too. So this is just a script, and I stored it in a file called test1. I can use a % symbol to comment that out, and then I could plot the other thing. So the other thing was this equation right here. See this equation? Let's plot that one out. Okay. So let's say this. Okay. Well, we could do both. So I'm gonna copy a few things to just have it and just plot both. Okay. So I'm copying these things down here. Okay. For the linear space, it's going to be y, and that's going to go from 0 to, I believe the height was 100. Yeah, I think the height was 100. I'm sorry, it goes right here, 100. And let's have 1,000 points. And then I have to multiply this by microns, 1e negative 6. That's in units of microns. I'm going to have another figure. I'm going to call that figure 2. So I'm going to pop up 2 figures. I still want the grid on. I want to clear. But my equation right here is going to be different. For my equation, I'm going to type in the other equation. And that was this right here. So 6 times some value in h minus y times y divided by h squared. Okay, so let's type that. So let's say my u mean was 10, and then there's like a 6 there. Okay, there was an h minus y. I have to define what h is because it doesn't know yet. And then that was times y. If you have like an array in MATLAB, these operations act differently if they're operating on vectors or scalars at a time. So you have to like put point times. It's kind of weird, but you'll get used to it. Okay, and then you divide it by, or point divide by h squared. And I have to say h that's going to be the height. And that's equal to 100 microns. Okay. So let's yeah, that looks okay. Let's plot it out to see what happens. Okay, so here's like two figures. So figure 1 is the first thing I plotted. Figure 2 is the profile. Okay, so this right here is the y-axis. Let me get back to my figure. I'm plotting from y equals 0 up to y equals 100 microns. So I'm plotting along this, okay? Okay, so as you go from here to here, the velocity profile goes up, so it's really high, and then it goes down to 0. So these are like the walls. So the velocity is 0 by the walls, right? And then in the middle, it's really high. So this is like a parabolic type of shape. Now this parabolic shape, this whole shape is being multiplied by this, okay? So it gets this really peak in the middle, I mean initially, and then it just tapers down to this. So after a while, whatever value this is being plugged into here, right? So what I mean is this 10 right here is actually whatever this equation is being plugged in right here. Okay, that's like the amplitude of that equation. Okay, so I just want to show you what's happening here. And again, you guys could put in your own profile, okay? So you're not, it doesn't have to be this one. All right, so let's get rid of these. And let's start COMSOL 5.5 and see if we can do it. Okay, so so first what you do, you start your model wizard. So you click on that, and then it's 2D. So you click 2D, and then you go to, I believe it's in fluid flow. Yeah, fluid structure interaction. So you expand that, and you want this one. This other one right here is fixed geometry. Okay, so you don't want that. And it has like a little picture here, and you can see like for this one, this structure just stayed straight, right? This one, the structure bent over. So you say that, you highlight that, then you add it. Okay, and it takes a second, or a few seconds. Okay, so it adds every physics you need for that. So you're going to end up with the fluid structure interaction. Here's the deforming mesh. Remember I told you about that? The ALE. The ALE? Yeah. Solid mechanics. So everything's loaded. So someone already made that package for us, which is great. So then we go to study. And for this one, we're going to do time-dependent analysis. Last Tuesday, we did stationary, right, where the fluid wasn't moving, right? We just looked at it at a certain point in time. Now we're going to look at an animation of the fluid moving in time. So we're going to do time-dependent, and then once that's selected, then you press done. And there you go. Okay, so now we're not going to do turbulent flow. This is going to be laminar flow. So this is going to be on the micro scale. So let's change the length unit to microns instead of meters. Okay, so when we change this to microns, everything is in microns now. That means every number that we enter into the parameters, if it has a length scale, it's going to default to microns. So we don't have to we don't have to use the square brackets and put micrometer in. If we want something else, then you use the square brackets. Then it overrides whatever the default length scale is. Okay, so we did that. So so let's start putting in our geometry. Let me just draw it over here so we remember. So here's our geometry. This was 100 microns. This was 300 microns. This right here had a width of 5 microns. The height, I believe, was what was that, 47.5 microns from their example. Okay, so we're going to do that. And also we're going to do the curve on the top. And for the curve on the top, we'll use fillets. So go to Geometry and click on Rectangle. And then that puts Rectangle mode here. And it also puts a rectangle under Geometry. So we're going to do 2 rectangles, but here's our first one. So for our first one, we're going to have a width of 300 microns. And remember, you don't have to put microns because you can see a micron right here. The unit's right there. And the height is going to be 100 microns. The base is going to be 0, 0. So everything's good. So then click Build All. And that should build your rectangle. And as you can see, the lower left-hand corner is at coordinate 0, 0. Okay. So the flute is going to be in there. So let's do the rectangle again for a second rectangle. So click on Rectangle. And this time it says Rectangle 2 for the label. The width of that rectangle is going to be 5 microns. The height is going to be 47.5. Now we're going to change the base, but before you do, just click Build All so you can see what happens. So as you can see here, when you click Build All, it puts that rectangle right here because the coordinate of that of its corner is at 0, 0. So we're going to change it. We're going to move the base over by 100 microns. So we put 100 there and then Build All, and then you can see it moved it from here all the way over to here. Okay. Now, as you can see, it has pretty sharp 90-degree vertices right there. We're going to round them out. Rounding out also helps with a lot of meshing as well, because typically when you have very sharp corners, the mesh density gets really high right there because COMSOL thinks a lot's going to go on. So it wants to try to get that more accurate and right. So you have a very high mesh density there. So we're going to use something called fillet. So see this right here? This is fillet. Okay, so you click on fillet, and then of course it puts it over in your model builder window. And it's turned on, but nothing's selected yet. So you're going to tell COMSOL which things you want to round out and smooth out. So you just go over and click on the points you're interested in. We're interested in this point right here and that point. So when you click on those, and mine happens to be 3 and 4, then you say what radius of curvature it is. So remember, this is 5 microns, and so if you were to blow this up right here, this whole thing is 5 microns, and you want to round this out, it's sort of like the radius you're interested in is half of that 5 microns. So we're talking about like 2.5 microns. Okay, for each of them. Okay, so let's type in 2.5 and then do Build All. And then you can see it's rounded now. And you can zoom in here to see what that's like. So I'm going to do the zoom box. I'm going to zoom in. Yeah, and it's rounded. Now, it doesn't have to be that way. You know, you can have different curvature. So, for example, let's just say you did 1 instead, and then you did Build All. You see how that is? So, it's up to you, right? It just depends on what kind of structure you're making. Let's do 2.5, Build All. Okay, and I'll do Zoom Extents. Okay, so the next thing we want to do is let's go to let's go to our moving mesh. Well, wait a minute. Maybe I should do that next. I mean later. Now let's go to our laminar flow. Okay, so let's go to our laminar flow here. And right now, we have to tell COMSOL, and we're going to do this for structures too. Right now, it doesn't know what's the fluid and what's the structure. So you're going to tell it. So if you click on this, it'll keep cycling through the different things. Gray is not chosen at all. If you click it once, it'll show up as here as 1. Okay. The other one was lit. If I click the structure part, that's domain 2, and that pops up. If I click it again, then it goes away. Okay. So just make sure that 1 is selected, or whatever domain you have. Your fluid may be domain 2. I don't know, but it's 1 here. So make sure that that is for your laminar flow. And for the structure, let's go down to structure, and then we'll say make sure that 2 is selected. So let's unselect 1, and then make sure 2 is selected, and it already is selected. Another thing you could do here is, like, let's say we did select 1. You can highlight 1 and just do minus, and then that will remove it. That's another way of doing it too. Okay, so we did that. Now let's go to materials. Okay, so first we'll do a blank material. We'll do 2 blank materials, one for the fluid and then another for the structure. And we're doing a blank material because we could load up our materials, but you can also key it in, so you need to know how to do that. Okay, so for the first material, that's just going to be the fluid, so we don't want this one, so let's get rid of that one. And here's what we have. It has density and dynamic viscosity. So the density of water, remember that was 1,000 kilograms per meter cubed, and for dynamic velocity, that is like 1e negative 6. I'm sorry, 1e negative 3 for dynamic viscosity. Yeah.
How did you get to that material, like on the left-hand side?
Oh, I'm sorry. Yeah, thank you. I right-clicked on material. Then I said blank material. Yeah. If you didn't want to do the right-click thing, you can go up to materials right here and do blank material right there. Okay? Yeah. So that's how I did that. And you just key in the values. Okay? Now let's do it again. Let's go up to materials. I'm going to right click on it, and I'm going to do another blank material. Now this is going to be for the structure. Okay, so nothing selected here. I'm going to select this, and it's asking for the Young's modulus. So let's put in 2e5, because it's 200 kilopascals, so 2e5 pascals. Poisson's ratio for a lot of things is a third for a lot of materials, and the density 7850 for the density. Okay, so the density is like almost 8 times the density of water. And the reason we need the density, because this is going to be a dynamic transient analysis, so it needs to know something about its inertia, its mass. So that's why density is being used here in these cases.
I'm having trouble actually selecting that when you just select all of them.
You mean like selecting 2 right here?
Yeah, it won't allow me to select that.
Oh, really? Wow.
Okay, no, go ahead. I'll figure it out.
Well, okay, so
I had to click select all, then click the minus box, the one that's on the,
Yeah,
on the right side.
yeah. So one thing, so if you do select all, if you click on here and then say select all, everything is sent in here, and then you can take out what you don't want, right? Or you could just keep cycling through, because like every time you click it, it will cycle through to like selecting it and then deselecting it, selecting it, deselecting it, right? So till you get to 2. Oh wait, okay, so I just clicked it again and it went away by accident. So I gotta click it back in there, 2 appears, and great, it saved my numbers. Okay. So is everyone caught up to where we are? Same, like clicking it, or? Really? I wonder if you guys are having a different problem than I'm having. Oh, what happened? Oh, okay.
You won't have but like a couple pixels to click on the actual structure. So if you
Oh,
more surface area to click on,
I see. I see.
that's the issue.
Okay, yeah, so some people were saying if you zoom, you have more area to click on. Huh? Oh yeah, so this is for, yeah, for that, it's 1,000 for the density, and viscosity is 1E negative 3. Yeah.
Still have the dynamic viscosity for the steel rod or whatever we did.
Really?
I have that Young's modulus. Yeah, like I have like the opposite. Material.
Wait, so go to material 1. What do you have there?
That is,
That's fine. Okay, then go to material 2.
that's the other one, this one.
But I wonder what do you have? Oh, did you go to here? That's material 2. And what do you? Well, what do you have in a laminar flow? That is interesting. Why? That's quite strange. I don't know why yours didn't. Okay, go to material 2 again.
Delete this one out of there.
Oh, what's
Or is
that?
that
For?
a linear elastic?
Oh, well, yeah, you don't have to like worry about that, but for like go to material 2 again. So you have viscosity. Why do you have viscosity there?
Yes, it's similar. Did you fix it?
I didn't fix it.
Oh, you have it for
Yeah,
for the water, right?
yeah, it's trying to have a Young's modulus and Poisson's ratio fluid.
Let me see this. It's so strange. I don't understand. Like, oops, not alert rim on the mouse. So that makes total sense. For material 2, you should not have these things.
Oh, now my undergrad texts me. Okay. Make your own time.
So, but,
Is it maybe because I selected all and deselected the other one?
That shouldn't be the problem. See, this right here,
Oh crap. I never saved Young's number. I gave him mine, but I don't know which one.
No, you just selected the water.
let's do the zoom in trick. That is so weird. I don't understand this. Okay, well let's. Okay, yeah, don't. I don't understand that. Okay, yeah. So one problem that someone was having is that in their when they click on their structural material, somehow viscosity showed up, which is kind of strange, and I don't understand how that happened. Does anyone else get viscosity along with Young's modulus? Or is this the only one?
They have maybe selected two materials in the solid
Well, that's what we were looking, and there's one. Yeah, this. That's kind of weird. I don't. Okay, so let's hope it doesn't break when we move forward. Okay, so let's move on. So we have the material, laminar flow. We have the structural mechanics. Now let's do the moving mesh. Okay, so for the moving mesh, let's look at our deformed mesh. So here we're going to select this right here. So one's going to be the deformed mesh. Okay, and then what we're going to do is go to our fixed boundary here, and then what we're going to do is select. Okay, so one thing you could do is click here and do Control A. It selects all the boundaries, and you're going to deselect these right here. Okay, this one, you may have to zoom in here. Okay, so let's do that. So this one's going to be deselected, that one's going to be deselected, and that one's going to be deselected. Because those are not going to be fixed boundaries. Yes? Oh, you do not have... so you do not have a moving mesh at all? Why would you not? Hey, in your model builder, did you do fluid interaction where it's not fixed for structure? Remember?
Is there any way I can go back and change or check that?
Okay, let's try this. Let me see your mouse. Let's do it this way. So let's go back here, new, here, 2D, and we're gonna go fluid structure. And you have two here, and this is the one you want right here. I think maybe this one doesn't have the moving mesh because it's not needed. I think that could be the reason. We'll find out right now. And then we'll go to study. Then we'll do time dependent. And then done. We don't want that one. Yeah, see? There you go. There you go. Moving mesh. Okay, so go ahead and do your microns. And then put in your geometry. So you got two rectangles. Yeah, go ahead and do your two rectangles real quick. Still there. Okay. All right, so okay, so that's selected. So this is going to be our moving mesh, and let's zoom back out. Right now, let's go over to our laminar flow, and oh wait, let me wait till someone gets caught up because they had to start over again. Hmm?
So for the material one, what is the problem? Material problem.
Oh, is that the dynamic viscosity?
Yeah.
That should be 1e negative 3.
Oh, see, mine doesn't even show that. This is strange because like it'll show from here through 202 and I have those properties in there.
data add.
Oh, wait a minute. You're having the same problem that he's having there.
I think we do. So if you can select the laminar flow, so you will select the material 2.1.
Oh, it should be 1. Yeah, it should be 1. That's the one that should be. Yeah, exactly. No, wait. Go to laminar. Okay, yeah. Should be okay now.
What about solid mechanics?
No.
Yeah. Go to solid mechanics. See what you have there. Oh, get rid of that one. Yeah, minus that one out. Yeah, there you go.
Okay, so then this needs.
Yeah, see, there he goes.
What was the number? What was the value?
Oh, I can show him.
Okay, cool. So how are you doing back here? Oh, do right click and then add blank material. Yeah, blank material. And then, yeah. And then a density. Oh, wait a minute. Wait. Something's wrong with this right here. Let's do, did you do this first right here? Okay, so this is what you want, and you don't want that. That's for laminar flow. For solid mechanics, you want this, but not this. So that's for that one. Now when you go in material, one, you only have 2 options, density and viscosity. So 1,000 here, 1 point E negative 3 there. And then 1 E negative 3. And then go to materials up here, right click again, and then do another blank material for your structure. And then click on 2. Yeah, there you go. 2E5 and 0.33, and then density 7850. Yeah, and you should be all set after that. Oh yeah, so moving mesh, go to deformation, and then click on 1, and sorry, you wouldn't need for that. And then go to moving mesh again, and then do right click, and then do your fixed boundary. And then go click right here, and do Control A to click everything, and then unclick your moving thing. Yeah, exactly. There you go. And then you're done with that. So now we're on laminar flow again. Okay, so I think you're all caught up. Okay, so now let's do our inlet. So we're going to pick inlet right here, and we're going to click here. Okay, and this is going to be our inlet. And for this, if you remember what we had back here, we're going to enter in this equation right here. Okay. I forgot what the equation was. Now we will define what H is, and then ComSol already knows what Y is, okay? And we're going to define out. We're going to define what U mean is, okay? So U underscore mean times 6 times H minus capital Y times capital Y divided by H squared. Oh, it is. Oh, can you guys see it up here? You can't see that? Okay, so yeah. So is u underscore mean. So yeah, we're going to actually define that. So u underscore mean times 6, okay, times quantity h, capital H minus capital Y, times capital Y divided by h squared. So h hat 2. Okay. Yeah, and it's red because it's complaining about it. It's like, what are these things here? Okay, so let's go to parameters, and we're going to key in what h is. So h, that was just our 100 microns. I guess we have to use brackets for this, for that parameter. I wonder why. Yeah, okay. Yeah, so bracket UM.
Square bracket?
Yeah, square bracket, correct. And and for our U here, capital U, and that's going to be 3.33 square bracket centimeters per second. Okay. And then we're going to right click on global, wait a minute. We're going to right click on global and go to and add variables. Okay. So right click on global definitions and add this new thing called variables. And for the variables, that's where we're going to put our u underscore mean. Okay. And that's going to be the expression that's going to have like the t squared and stuff. So I'm going to write it bigger over here. Now for here, we have to do our units, okay? And the seconds hat squared. Oops. Yeah. Times t hat 2, okay? Not done yet. Plus, I'll continue right here, plus 0.0016, and then square bracket to the 4th power. And then parentheses. That parentheses goes with the square root. So all that's under square root. So this whole thing right here has units of seconds to the 4th power. So that's why you have this for that number, and you have this for that number. Okay? Because that's going to be multiplied by seconds squared. So then you're going to have seconds to the 4th there, too. Okay, so that needs to be typed in for this profile. Again, you could have chosen a better one or easier one, but this example is using this. So t squared divided by square root, then is t to the 4th minus 0.07 square bracket s hat 2 square bracket times t hat 2 plus 0.0016, and square bracket s hat 4, square bracket, and then ending parentheses. Okay. Huh? The y parameter? Oh, in the last expression? Yeah, that y is actually a COMSOL variable. So COMSOL already knows what it is. Because here's what I think will happen. I think it'll turn red if I try to define it. Yeah, see? It turned red, because that's one of COMSOL's own variables. So if I would have said y1, then it would be okay with that, right? Yeah, but good observation, though. Okay, we all set here? Okay. All right, so those are our variables. So now what we can do is go to our inlet down here. So our inlet. Now you see here, now it's no longer red. It knows what H is. It knows what U mean is, because we defined it up here in our, in our variables. Here's our U mean. And here's our parameters. Okay. Now for the laminar flow, let's do an outlet. So right click on the laminar flow, then go to outlet, and then click right here. And the pressure is already defaulted to 0, so we're fine with that. So that's all we need to do, just tell it what the outlet is. Now let's do structural mechanics. So for structural mechanics, all we need to do here is define, so I right click on structural mechanics, and then I put a fixed constraint. And the only fixed constraint is this one right here at the bottom. So you click on that, and on mine that's boundary number 5. Okay? Everything else can move in the structure, but not the thing that's holding it to the sidewall. Okay? Now let's go to, so we did the movie mesh, we did those. I think next we just need to go to the mesh. So click on the mesh, and then right click, and then say free triangular. So this is our kind of mesh we need to use for the moving mesh. Okay, and then what we're going to do is we're going to do the entire geometry. Okay, and you can do build all to see what happens. As you can see, it does build all. But look at how the mesh is, because we're going to change it a little bit. So let's go to size. So click on size, and then instead of saying calibrate for general physics, we're going to calibrate it for fluid dynamics. There's also plasma and semiconductor, okay, but we're going to calibrate it for fluid dynamics, and you'll see what happens to it. Oh, and also for the mesh size, instead of normal, let's do fine, because it's a lot's going on. So then do another build all, then you can see how it's different. Okay, everybody got that? Okay. Now you should be ready to compute. I think we did everything. So go to study. So for the oh wait, don't press compute yet. Did anybody press compute yet? Okay, so what we're gonna do? So remember that funny plot that we had initially, where it went like this in time. It did something really quickly, and then it tapered off like that, right? A lot of transient is happening right here. So when we compute our solution, we want to be very careful as we step through here, okay? After a steady state, not much is happening, so then we could jump in time huge amounts because nothing's really happening. Okay, so we're going to do that with range. And that's really important because a lot of times when you guys are simulating things, if something is happening rapidly, you want to time step really slow through that. And as things taper off like there where nothing changes, then you have larger time steps. So for that, let's do a range like this. So click this and you can change your range. Okay, as start, step, and stop. So our start is 0. The step we're going to make is 005. Ours even, yeah, and then we're going to end at 0.75. I'm sorry, 0.75. So basically, that's going from 0 to maybe like right here, 0.75. And each little time step is like 5 milliseconds. Okay? So then you click replace. And once you click replace, it replaces the old range with this one. So that's just the first time steps. Now let's do it again. We're going to do another range for the rest. So there, instead of starting at 0.75, we're going to take these large time steps of a quarter second. And so we're going to start, the next quarter second is at 1 after 0.75. And the step is going to be 0.25. And we're going to stop at 4 seconds. Okay? And instead of saying replace, we're going to do add. And when you add it, it leaves the first one there, and then it has the second one. Okay? And then for the tolerance, we're going to have a finer tolerance. So let's use our user-controlled tolerance. And instead of it being defaulted to 0.01, let's have 0.003 zeros. Yeah. So 1e negative 4. That's the relative tolerance here. Try to do like a really good job. Okay. Now you should be able to compute if everything went well. I'm not sure about yours. So it should take about a minute to do, because, and the reason why, because think of all the things it's computing here. Oh, did someone get something?
Convergence plots.
You have a convergence problem?
Yeah. No plots. Convergence plots.
Oh, yeah. Yeah, the other tabs here. Yeah, so what they're looking at are these other tabs right here. And you can see like how it's progressing. So a lot of times if your simulation isn't converging nicely, you might want to see like where it's happening, and then you could change things around there, like change the time steps or change, just various things about it, like what's happening disturbance-wise around that time. Okay, and also you can see a bar right here too. So there, you should have something like this. Oh, good, yeah. All right, you got it. So yours did work, even with mu. Oh, it's good now. Okay. So, everyone good? Okay, cool. So we survived. Okay, so all right. So let's look at some analysis. Okay, because plotting it out is great, but you want to see what's going on. So in our 2 minutes that we have left, let's do this real quick. So you can look at velocity. Velocity is being plotted right now. Okay. You could look at pressure. If you click on pressure, it shows you what's happening with pressure. Okay. And those are like, I think those are equipressure contours. And also what's happening with stress. So stress, we know what's happening with your structure with stress. So for example, if you go to velocity, you can do a right click and then do a streamline. Okay. And then with that streamline, this is something that we actually did before. If you plot that out, then you'll see, oh, wait a minute, I need to do, I forgot to select my boundary. Yeah, sorry about that. So, I need to click here at the bottom here, and I just need to choose what boundary the streamline start on. So I can choose this boundary right here, and that shows 1. That's boundary number 1. Then I plot that. Then it shows my streamlines. Okay? Now, something really interesting happens right here, and you don't see it with these streamlines, right? Because they start here. But you can start a streamline anywhere you want. So let's start a streamline right in there. And let me show you how to do that. So go to, see where it says positioning, and it says on selected boundaries. We want to change that. Let's do it from start point controlled, okay? And then the entry method, let's say coordinates. I can choose a coordinate, okay? This coordinate right here, it goes over X like maybe 125 and maybe up Y like 10. So I'm going to put for X, I'm going to put 125 microns. And then for Y, I'm going to put 10. And then if I plot that, oh wait a minute. This is really dark. So let's change the color to red. And then plot that. See? Here's the, how come you're, can you see that? Okay, let's do white. How's that? Is that better? Wow, this is really bad contrast. It looks perfect on my monitor. Okay, what you should see is a circular path right here. That's what you should see. Where that's the streamline. So it starts at one point and it streams around like that. Another thing we can do is animation. So if you go to animation and then do your player, then you can show your animation, right? And you could do that for pressure too, right? So you could do your animation for pressure as well. Yes, see how your pressure, and you can zoom in around there. Like let's say we do something like that, and we play that. You could also put it on repeat as well as you play. Okay, so we're a couple of minutes over. So so what you guys should do is, this is a really good example of, now that we're getting going with multiple physics, looking at different things. So what I'm going to have you guys do is, since it's like a Thursday, what we could do is like do an assignment every Thursday, because then we have like 4 days to give you guys time to play around with it. So go through this example again and try something new. Like maybe try something like, maybe put like another structure right here. Maybe, I don't know. Or maybe a hole in there. I don't know this, but just first try what we just did. Okay, then once you get the hang of it, then try to change it around a little bit, right? So just try that, and so next Tuesday, at least we'll have this type of model mastered. Yeah. Okay, yeah, I'll do that. Yeah, because because like in the video, maybe not everything is like really clear in the video, even though the videos are going to be online. I'll do like step by step. So I'll add that to the lecture notes, put that online.
Also, that way, include copy and paste solutions on the same line.
Yeah, that'll be good. Yeah, good idea. Okay, guys, see you next Tuesday.